Whoops. I thought I was 10 minutes later, but fine as well. So this is me. As you can recognize, I'm a computer scientist. I like airplanes. I like fixing things. And this is basically why I ended up in the digital MRO business. And with this background, I want to tell you today about a research project, a state-funded research project that we did called RTA-PHM, where we investigated data-driven service platforms with UAVs. And we already recognized at the beginning of the project that we would end up with a bootstrapping project, a problem with for our AI algorithms. And I also want to talk briefly about the solution approach that we did there, digital twin first. And I will end my talk with some results and some lookout for future work. So RTA-PHM, a very cryptic acronym, but it stands for Real-Time Analytics, Prognostics and Health Management. The vision of the partners that you see here was basically a world where you have, or a city, where you have a fully automated urban air services with autonomous drones, automated infrastructure, a digital platform, which is orchestrating all the services, and some enabling technologies like artificial intelligence. Of course, we had to break down this very broad vision into a manageable use case, and we chose organ transport involving UAVs for the last miles, basically from the hospital to the next leg. So the idea was really that the doctors, whenever an organ became available, could enter this information into a service platform, and 1 hour later a drone would land and pick up the organ. Within the group, we focused on the software architecture of such a platform and on the enabling integrated health management technologies, IVHM technologies, including also predictive maintenance in order to make very reliable service commitments. And our core contribution in this project was to basically provide a fleet of virtual UAVs to provide digital twins. And we researched into tooling in order to assemble these digital twins with some deliverables coming from the partner. So why would we actually need this? This is basically the bootstrapping project problem that we identified in the first place. So let's look a little bit into the actual research focus that we had. We have a digital service platform, and we have a fleet of UAVs flying around. And the idea is that these UAVs basically can diagnose themselves. We do not do preventive maintenance, at least not for all of the components, but some of the components basically can tell about their state. And through constant monitoring, we would generate a constant data stream of health data that is fed into our digital platform. And based on this data, we would be able to do maintenance predictions. Basically, when would the maintenance be due? And this information, along with a lot of other information, would then go into a component that calculates the service commitment that would be finally presented to the end customer. But of course, the components that we were investigating that did not exist yet, so we did not have any data for exploration or training available. So a part of the research group basically took over the job to provide us with high-fidelity simulations for these components that we could assemble into a digital twin even before we had the actual product. So to be used basically for generating an initial set of training data. Of course, whenever you have then the in-service data available, you would go into refinement. And in order to provide a good habitat for these simulation components, we coupled and we basically also integrated basically standard flight simulator software in order to simulate these components. And basically, so we overcame the initial bootstrapping problem. Whenever you have to do with simulation, there are a lot of questions to be asked to the guys who actually produce the models. How representative is your model? Is it really valid? Have you tested that? So these questions, of course, had to be answered by the modeling guys. We were more confronted with questions. How do we protect our intellectual property, for instance, when we provide one of our models in the compound? In what form should I give this model into the project? How can I test nominal versus faulty behavior? All these questions basically relate to integration issues. And as a software company, we do not like to do repetitive tasks, so we came up with a tool set and a tool chain which allowed us to basically automate the integration process of this digital twin. As input, you could basically use the models, the diagnostic algorithms, and of course the flight simulator software. In this case, we used a combination of Gazebo and PX4. That's an autopilot for drones. We started off with a set of command line tools and soon realized, okay, we have to provide some development environment, some graphical user interface. And this is basically what the end product was that we delivered in the project. And we also could give this to the model developers so that they could do very soon repeated and integrated tests with their models. Yeah, and the outcome of this tool, fully integrated, is a digital twin that you could execute also on cloud-based technologies. This is a screenshot from the final demonstrator. We have on the left side basically the system simulation in closed loop integration with the flight simulator, basically producing the initial training data. Just some highlights how it actually works. Some more details we were happy to talk to you at our booth, of course. We expected Simulink C exports for now. And the tooling is basically able to generate all this glue code around the models, responsible for parameter exchange, for timing, for synchronizing it with the flight simulator, and so on. And we also were able to provide some debugging features for the developers. Also, you want to produce a lot of data as fast as possible, so we took care of some IT aspects like parallel computing to basically use the CPUs to its best. And we also were able to do scripting, which allowed us to generate the data in an already tagged, sorry, my voice is failing, in an automated tagging, which is really useful for AI technologies. So, what was the outcome? Basically what you see on the right, using some fault injection mechanisms, we were able to stimulate the models so that they could really, sorry, thank you. Sorry, must have picked up some virus or whatever. And of course, we identified a lot of further use cases that we could integrate with our toolchain. Just some last words. Future work, integrating with the asset administration shell is something that we want to pursue. And integrating with the functional mockup interface, sorry. So, sorry for the voice problems, but we are happy to answer your questions later at our booth A0. Thank you very much.